Welcome to AI Frontiers. Today, we're exploring Seeing the Future, Computer Vision Research, based on 120 papers from May 29, 2025. Join us as we examine how machines are learning to understand the visual world in increasingly sophisticated ways. In this presentation, we'll explore the cutting edge of computer vision research across several dimensions. We'll examine the dominant research themes driving innovation in the field and analyze breakthrough findings from 120 recent papers. We'll highlight the methodological innovations propelling computer vision forward, identify future directions and emerging opportunities, and showcase 3 seminal papers with transformative potential for the field and its applications. Before diving into specific research, let's establish a field overview of computer vision. This discipline enables machines to derive meaningful information from visual data like images and videos. The field has evolved dramatically from basic pattern recognition to complex scene understanding and reasoning. Computer vision sits at the intersection of artificial intelligence, machine learning, signal processing, and cognitive science. It powers diverse applications ranging from autonomous vehicles to creative content generation. Modern computer vision increasingly integrates with language understanding, 3D spatial reasoning, and higher-order cognitive capabilities, moving beyond simple recognition tasks toward more human-like visual intelligence. The first major research theme we'll explore is vision-language integration. This represents a fundamental shift toward bridging visual and textual understanding in AI systems. Mann and colleagues introduced Argus, which implements visual attention grounding for improved multimodal reasoning. This approach explicitly connects reasoning steps to relevant regions in images, ensuring the model's understanding is properly anchored in visual reality. Wang and colleagues developed Pixel Think, optimizing chain-of-pixel reasoning specifically for segmentation tasks using multimodal large language models. This approach streamlines the reasoning process by focusing on relevant spatial regions. This integration of vision and language enables explanation, question answering, and instruction following capabilities that were previously unattainable. The approach mimics human cognitive processes by combining visual inputs with language and contextual understanding. This represents a shift from treating computer vision as an isolated discipline to viewing it as part of a broader multimodal intelligence framework. The second major research theme focuses on 3D scene understanding, moving from 2D observations to comprehensive 3D representation. Zhang and colleagues introduced AnySplat, a revolutionary approach for feed-forward 3D Gaussian splatting from unconstrained views. This technique predicts 3D Gaussian primitives and camera parameters in a single forward pass, eliminating the need for pre-calibrated camera poses or per scene optimization. Bardati and colleagues developed Physics NeRF, which incorporates physical constraints to improve 3D reconstruction from sparse viewpoints. By integrating physics-based priors, their approach achieves more realistic and consistent reconstructions even with limited observations. These advances are critical for applications in virtual and augmented reality, robotics, and immersive content creation. They represent significant progress toward real-time 3D understanding from casually captured images, making sophisticated 3D reconstruction accessible for everyday use cases without specialized equipment. Our third research theme combines visual reasoning capabilities with efficiency improvements. Yang and colleagues created MMSI-Bench, a comprehensive benchmark for evaluating multi-image spatial intelligence in multimodal large language models. This standardized evaluation framework covers tasks such as relative positioning, spatial transformations, and multi-view consistency. Wu and colleagues enhanced spatial reasoning from purely 2D observations with Spatial-MLLM, introducing a dual encoder architecture that combines semantic features with 3D structure features. On the efficiency front, Wang and colleagues addressed scalability challenges in 3D models with Z-pressor compression, identifying representation bottlenecks and developing targeted compression strategies. Sain and colleagues optimized network efficiency specifically for human sketch recognition by leveraging the sparse and structural nature of sketches. These developments reflect dual trends toward both higher-order reasoning capabilities and practical deployability, ensuring advanced vision systems can operate effectively in resource-constrained environments. The fourth research theme encompasses generative vision and domain-specific applications. Jung and colleagues repurposed diffusion models for low-light enhancement with dark diff, adapting generative techniques to recover details and natural colors from underexposed raw images. Dalva and colleagues enabled multi-concept image editing without retraining through LORA Shop, which leverages feature interaction patterns in diffusion transformers to enable disentangled editing of different concepts within the same image. Moving to specialized applications, Liu and colleagues introduced EndoBench for evaluating AI models in endoscopy analysis, providing a comprehensive benchmark across the full spectrum of endoscopic practice. Shabir and colleagues developed ThinkGeo for assessing AI capabilities in remote sensing tasks, with standardized protocols for evaluating change detection, land use classification, and environmental monitoring. This diversification reflects the field's maturation from generic capabilities to specialized applications tailored for specific domains with unique challenges and requirements. Across these research themes, several breakthrough findings are shaping the field's trajectory. Kai and colleagues demonstrated that vision language action models significantly improve autonomous driving performance in challenging edge cases, precisely where current systems typically fail. Zhang and colleagues showed that feed-forward 3D reconstruction can eliminate the need for camera calibration and optimization while maintaining high-quality results, dramatically reducing technical barriers to 3D scene reconstruction. Dalva and colleagues achieved multi-concept image editing without retraining through feature disentanglement, effectively turning personalized diffusion models into practical editing tools. Wu and colleagues demonstrated that spatial reasoning from purely 2D inputs can reach comparable performance to 3D-based approaches, making advanced spatial intelligence more accessible. Domain-specific benchmarks have revealed substantial performance gaps between state-of-the-art AI systems and human experts, highlighting critical areas for improvement in specialized applications like medical imaging and remote sensing. Several key methodological approaches are driving innovation across these research areas. Multimodal architectures combining vision encoders with language models enable sophisticated reasoning across visual and textual domains. Neural rendering techniques, including neural radiance fields variants and 3D Gaussian splatting, are advancing novel view synthesis and 3D reconstruction capabilities. Diffusion models are being adapted and specialized for image enhancement and generation tasks beyond their original content creation applications. Chain-of-thought reasoning and attention mechanisms are being developed to ground visual understanding in specific image regions, improving the precision and explainability of visual reasoning. Physics-informed neural networks are incorporating domain knowledge as constraints, improving performance in scenarios with limited data by leveraging fundamental physical principles. These methodological innovations collectively enable more capable, efficient, and specialized computer vision systems. Let's examine our first selected paper in detail. AnySplat. Feed-forward 3D Gaussian splatting from unconstrained views by Zhang and colleagues. This work introduces a revolutionary approach that predicts 3D Gaussian primitives and camera parameters in a single forward pass of a neural network. The technique eliminates several major bottlenecks in 3D scene reconstruction. It doesn't require pre-calibrated camera poses, doesn't need per-scene optimization, and scales efficiently to both sparse and dense view scenarios. In extensive zero-shot evaluations, AnySplat matches the quality of pose-aware baselines while significantly reducing rendering latency compared to optimization-based approaches. This breakthrough could enable real-time novel view synthesis from casually captured photos or videos, transforming applications in virtual reality, augmented reality, and content creation. AnySplat was selected for our spotlight because it fundamentally revolutionizes 3D scene reconstruction accessibility and efficiency, making immersive 3D experiences possible from everyday visual content without specialized expertise or equipment. Our second selected paper is LORA Shop. Training Free Multi-Concept Image Generation and Editing with Rectified Flow Transformers by Dalva and colleagues. This work introduces the first framework for multi-concept image editing with low-rank adaptation models without requiring retraining. The key insight is the discovery of specific feature interaction patterns inside diffusion transformers, where concept-specific features activate spatially coherent regions early in the denoising process. This finding enables a novel approach where disentangled latent masks are derived for each concept in a prior forward pass, allowing the blending of corresponding LoRa weights only within regions bounding the concepts to be personalized. The result is seamless integration of multiple subjects or styles into original scenes while preserving global context, lighting, and fine details. LoRa Shop was selected for our spotlight because it transforms personalized diffusion models into practical editing tools, effectively creating a Photoshop with LoRa's capability that dramatically lowers barriers to complex creative image editing. Our third selected paper is Impromptu VLA. Open Weights and Open Data for Driving Vision Language Action Models by Kai and colleagues. This work introduces a comprehensive dataset of over 80,000 meticulously curated video clips, distilled from over 2 million source clips across 8 open-source datasets. What makes this dataset particularly valuable is its focus on challenging unstructured driving scenarios, precisely the edge cases where current autonomous systems tend to fail. Vision language action models trained with this dataset show substantial performance gains on established benchmarks, improving closed-loop neuro-NCAP scores and collision rates, while reaching near state-of-the-art accuracy in open-loop trajectory prediction. The open release of both the dataset and model weights creates an opportunity for accelerated progress in autonomous driving research. This paper was selected for our spotlight because of its integrated approach to perception, understanding, and action coordination, providing a template for how complex embodied AI systems might be designed in domains where these capabilities must work together seamlessly. Looking toward the future, several clear research directions are emerging in computer vision. We anticipate deeper integration of vision with language, reasoning, and physical understanding, moving toward more holistic AI systems that combine multiple cognitive capabilities. More efficient architectures will enable deployment on resource-constrained devices, making advanced computer vision accessible across diverse hardware platforms. Enhanced generative capabilities with greater control and compositional flexibility will transform creative applications and content creation workflows. Domain-specific optimization will continue for critical applications in healthcare, environmental monitoring, and safety systems, addressing the unique challenges and requirements of each field. A major focus will be bridging performance gaps between AI systems and human experts in specialized domains, particularly for tasks requiring domain knowledge and contextual understanding. These directions collectively point toward more capable, efficient, and specialized computer vision systems that can operate effectively in real-world environments. A brief note on how this presentation was created. The content was synthesized using GPT and Anthropic's Claude 3-7 Sonnet 20,250,219 model, with text-to-speech synthesis performed using Google's advanced TTS technology. Visual elements were generated using OpenAI's image generation capabilities. While the synthesized content was reviewed by human experts for accuracy and coherence, some oversights may exist in the comprehensive analysis of 120 papers. All references to specific research have been provided based on the information available at the time of creation. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses content under its API terms of use. AI Frontiers is not affiliated with or endorsed by the arXiv preprint server.